Today we're going to talk about section 3.2 in your book on differentiability, which is the ability for a function to have a derivative at a particular point. You might be wondering, why isn't it called derivative ability? I can't even say it, okay? But it's to remind you that when you are doing a derivative, you're taking the differences. It's the difference in y over the difference in x. So that's the root of why that's called differentiability and not derivative of, I can't say it, derivatability. So what are some of the ways where f prime at a might fail to exist? Well, if this limit, the limit is x approaches a of f of x minus f of a over x minus a, remember that is the alternate form of the derivative. If that limit fails to exist, well, then you don't have a derivative at that point. We're going to look at several different examples of this. So here's the first example. Y is equal to the absolute value of x at x equals 0. So let's take a look real quick at what happens as we approach 0 from the left and what happens as we approach 0 from the right. Which would be the same thing as if we did, the limit as, we could have also done the limit as h approaches 0 from the right of f of 0 plus h minus f of 0 over h. It's the same thing. Okay? So, as we're approaching from the left for this one, so I have a point at 0 and a point over here. As these points move closer towards 0, what are all the slopes? -1. And then over here, as these points approach 0, what are all the slopes? 1. Therefore, the limit as x approaches 0 of f of x minus f of 0 over x minus 0 does not exist. This is an example of a corner. Okay, some books call it a sharp corner. We even have seen on the AP exam things like a sharp point. I'm like, well, a point is like a dot, so I'm not sure how that can be sharp, but I know what they were trying to say. And at different times, different things have been accepted. The best answer is to say that the left-hand derivative and the right-hand derivative at 0 do not agree, or are not equal to one another is even better. Therefore, the derivative at x equals 0 for y equals the absolute value of x does not exist. Okay? All right, so let's take a look at this next one. Y equals x to the 2/3, or f of x equals x to the 2/3 at x equals 0. This is a little more difficult. It's like, well, so what is the limit as x goes to 0 of this? Let's look at a better graph than my hand-drawn graph for this. What? You laughing at my hand-drawn graph? Let's erase all this stuff. Let's look at y equals x raised to the 2/3 power. Apparently I didn't type that in right. Got to do parentheses, yep. All right, and then let's zoom in. So now we're way zoomed in. What sort of slopes, if I'm coming from the left side, what sort of slopes am I getting? All lines are straight, so let's not ever say straight line again in my presence. What do you mean by a straight line? You don't mean straight, you mean something else.
Almost a straight slope.
Oh, stop saying straight.
Okay. Almost vertical.
There we go. There's the correct term. It's almost vertical, but it leans slightly to the left, so it is a negative, right? This goes down as it goes from left to right. So this is going to negative infinity, while on this side it's going to, pardon?
Infinity.
Positive infinity, exactly. Again, the left and right hand derivatives don't agree. And even if they did agree, they're infinite. That isn't a value. So this is an example of something that's sometimes called a cusp. Okay, between those two things. So there was an error opening this document. This file cannot be found. It's right here. All right, let's take a look at this one. F of x is equal to the cube root of x at x equals 0. Well, let's take a look at that one as a graph. There are some days when you're like, what do you mean you can't be opened? It's already open. Let's look at, get rid of this graph. Yeah, it's having all kinds of trouble today. There we go. Should have. So the cube root is x to the 1/3. You're like, where's the graph? Well, it's there. Zoom out a little bit. Oh, look at that.
That's not a very nice color. That's a beautiful color.
Yeah, it's a difficult color to see. Let's options, graph paper, color, monochrome. Happy now? Does make it easier to see. What's going on there? From either side, what kind of slopes are we getting? They're positive slopes on either side, and they are practically vertical, correct? So as we move closer to 0 from either side, we're going to get positive infinity. It's an ergonomic chair, yeah. So this is an example of a vertical tangent. Okay, it's got a vertical tangent line there. All right, now let's take a look at this one. We've talked about this a little bit. So this is f of x is equal to -1 for x less than or equal to 0, and 1 for x greater than or equal to 0. This could also have been written as this. F of x is equal to the absolute value of x over x for x less than 0. It's equal to 1 for x equals 0. And it could be back to absolute value of x over x for x greater than 0. Right? So, looks like this. As we're approaching 0 from the left, my slopes are going to look something like this. Right? So I'm doing the slope between those 2 points. What kind of a slope does that have? Positive, and as this moves closer to 0, they're going to be going to, I'm sorry?
The abyss.
Yes, the slopes will be getting closer to what? Infinity. Whereas over here, I'll do these in red. Not that you'll be able to see them because, well, let's do them in yellow so I can see them. So if I'm at a point here, or green, whatever color that is,
That's yellow.
what kind of slopes are these?
0.
0. This is what happens when you have a discontinuity. The slope from one side does not match the slope from the other side. The slope from one of the sides when you have a discontinuity is almost always infinity, assuming that the function is defined everywhere. If it's not defined somewhere, then this whole thing becomes moot because you can't find f of 0 if there's just a hole there, so you can't find the derivative. So those are 4 ways that you can have something that is not differentiable. And basically it all boils down to either the slope is undefined because it's vertical, or the slope from the left and the slope from the right don't agree with one another. Okay? So, page 2. If a function has a derivative at x equals a, then f is continuous at x equals a. Right? If it's got a derivative, the function had to be continuous there, because if the function is discontinuous, we don't have a derivative there. But it doesn't work in reverse. Continuity does not imply differentiability. Just look at our first example. Actually, our first, second, and third examples. All of those were continuous functions, but none of them were differentiable at x equals 0. So if a function is differentiable at a particular point, it is automatically continuous at that point. But the converse of that is not necessarily true. Just because a function is continuous at a point does not mean that it's differentiable at a point. Now, how does that come up? Well, there are several times on the AP exam where they will tell you, as part of the stem of the problem, that a function is differentiable for all x. But what you need to justify your answer is that the function is continuous for all x. So you have to put in there, since the function is differentiable for all x, it is then therefore also continuous for all x. Okay? That comes up a fair bit on free response questions. So if a function f is differentiable on an interval, then f prime is continuous on that interval. And then the intermediate value theorem will apply both to the function and to the derivative. So, let's find all points in the domain of f of x is equal to the absolute value of x plus 3 minus 4. Find all points. That sentence doesn't make good sense. Find all points in the domain of this where f is, oh, let's not do that color for this.
Why is it writing with that hand?
It switches every now and then, and I don't really know why. I find it particularly annoying.
Maybe you click on the pen.
All right. Well, regardless,
What if you click on the pencil, like on the little box
on the pencil
on the very front?
here,
Yeah, right there.
yeah, I am. And now it's this one. I mean,
I'd rather have that than
yeah, drawing with the hand is a little strange. All right. So we know that this function is just the absolute value function. How has it been shifted?
the hand though. 3. Shifted 40 off to the left. Yeah.
It's been moved 4 down and what? 3 to the left. So this is not differentiable. At the point -3, -4. One of the other things that happens is that if a function is differentiable at a point, it is locally linear. What that means is that if you were to zoom in on the tangent line at a point, the graph of the tangent line and the graph of the derivative, the graph of the function and the graph of the tangent line would become indistinguishable from one another if you zoomed in enough. That makes sense? Yama, you look like you're not certain. Are you sure, really? No? Okay. Yeah, let's get this off of this. All right, so let me show you what I mean by that. Stop doing that. Oh my goodness. I do not know why it won't. Weird. All right, let's get rid of this. Let's do it that way. That's a lot easier. All right, so let's do a really simple function. Let's do y is equal to x squared. Okay, and I happen to know that the tangent line for this at x is 1 is y equals x minus 1. Yeah, I don't know that. Do that again. It's y equals x. Nope. I'm being stupid. Y equals 2x. And there's where the minus 1 comes in. Y equals 2x minus 1. I'll get it right in just a second. There we go. Okay? All right. So what I'm saying is if we zoom in on this point right here, so I'm going to change this, go from 0 to 2 and 0 to 2. Do you see how the tangent line and the graph are almost exactly the same? And now that I have that centered, if I zoom in on it, can you even see that there's 2 anymore? No, it's because the graph is locally linear. If you get small enough, it looks like a line. See, if you had a circle that was big enough, that was drawn someplace, and you only got to look at a little piece of it, it would look straight. You wouldn't be able to tell that it was curved. Hence, some of our friends in the Flat Earth Society.
They do tangent lines of the Earth.
Yeah, part of the problem is the Earth is so big that, locally the ground looks, It's straight, right? Obviously, this is flat.
Duh.
Yeah. All right. So if f prime of a exists, we can estimate its value by finding the average rate of change on a small interval containing a. Now, this particular one is an interval to either side, and it's symmetric. So we went plus h to one side, minus h to the other side. So we said we're going to do a really small interval, and we're going to go 0.01 to the right of A and 0.01 to the left of A, and find the slope. So this is called the symmetric difference quotient. The reason it's called the symmetric difference quotient is we went the same amount to either side of A. It's very accurate for small values of h if the derivative exists. Notice that if has been underlined multiple times there. That's kind of important. All right. So if f of x is equal to x to the fourth minus 3x squared, find the numerical derivative at x equals 5 using h is 0.001. And we're going to use the symmetric difference quotient. So what we're going to do is say that f prime at 5 can be estimated by doing f of 5.001 minus f of 4.999 over 5.001 minus 4.999. Which is something you would definitely want to use a calculator for.
You don't know it off the top of your head?
No, I don't even know it off the bottom of my heart. So here's what I want. I want 5 point, actually, yeah, let's go ahead and put them in parentheses. It doesn't really matter. 5.001 raised to the fourth minus 3 times 5.001 squared minus 4.999 raised to the fourth minus 3 times 4.999 squared all over 5.001 minus 4.999. It's really close to 470. And if the derivative exists, that's a really good approximation. Your calculator can do this without having to type all that junk in. Here's how it works. If you go to the math menu, scroll down to number 8. This is the third thing you have to be able to use a calculator for on the AP exam. Remember, the first two are graph in an appropriate viewing window, and second, be able to solve an equation. The third thing is be able to find a numeric derivative. So, in numeric derivative. It asks you what you want to take the derivative with respect to. Our variable is x. This is x raised to the fourth minus 3x squared and we want the derivative at, that means evaluated at, that's horizontal piece right here, evaluated at x equals 5. Bada boom, bada bing. Hey, it's the exact same number because your calculator uses 1/1000th for the change in either direction. It's a really good estimate. Okay, you need to be able to do that using your calculator. That's what we just did. Depending on your calculator, yours says in deriv like that. Sometimes you'll see it in books written as ender like this. Either one is fine. Now, we can actually use this to help us figure out a derivative. So for example, if y is f of x is the natural log of x, we can actually graph the numeric derivative of that. So that's math 8, the numeric derivative, so the derivative with respect to x of, if this is particularly complicated, you could actually use your alpha trace to just say, put in whatever I had in y1, which is helpful. And where are we calculating the derivative? Wherever the pixel happens to be, at whatever x value it happens to be at. So at x equals x. So I'm going to do zoom standard because I have no idea what I was looking at before. There's natural log of x. And there's the numeric derivative. Now let's see if we can guess what this is. And I think I'm going to look at the table to help me out. So when x is 1, the derivative is 1. That's interesting. When x is 2, the derivative is 0.5, which is better known in fraction form as 1/2. And when x is 3, the derivative is 0.333, which is, please, 1/3. And when it's 4, the derivative is, when x is 4, the derivative is 0.25, which is, are we seeing a pattern here? It's a pretty solid pattern. Exactly. So, what does that mean? F prime of x is 1 over x. The derivative for natural log of x is 1 over x. Have we proved it? No. Are we pretty darn convinced? Yes. Okay. Any questions about that? All right, then that is it for today.